Welcome back. The objectives of this video are to introduce the complex plane, to find the absolute value of a complex number, and to find the trig form of a complex number. So let's take a look at the complex plane. The complex plane is identical to our real number plane. However, the horizontal axis is our real axis where we will plot the real portion of our complex number, and the vertical axis is the imaginary axis, and we'll use that to plot the imaginary portion. So a number like 3 plus 2i, we would go 3 units out on the real axis and 2 units up on the imaginary axis, and we would plot that point. So we still have our quadrants with positive, 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 or negative, positive, and so forth. So we would have this kind of thing in our quadrants. So our third quadrant is still negative, negative, where the real part is negative and the imaginary part is negative, and so forth. We would plot a number like negative 2 minus I, negative 2 on the real axis, and negative 1i on the imaginary axis. Our second objective is to find the absolute value of a complex number. A plus bi is our complex number, and it's defined as the distance between the origin and the point AB, where A is our real part and B is our imaginary part. So this looks a lot like your distance formula. So the absolute value of A plus bi is simply the square root of A squared plus B squared. So we'll denote that as R equals the square root of A squared plus B squared. So if we want to find the absolute value of a complex number, our complex number here is z. It's negative 2 plus 5i. If we wanted to find that particular location on our imaginary coordinate plane, we might look at that as negative 2 on the real part and 5i, 1, 2, 3, 4, 5, on the imaginary part, and we could plot that. So our distance is our distance r from the origin to our particular point. We would find out what that is. So we want to find that absolute value. So r is simply the square root of a squared plus b squared. So we don't include the I here. So r is simply 4 plus 25, or r is the square root of 29. That's our distance from the origin to our point that we plotted here. Our next objective, our final objective 3, is to find the trig form of a complex number. We have our imaginary axis and our real axis, and we have our point AB. Just like we saw on the real number line, or the real coordinate plane, our x values, or our a values, are cosine, and our y values, or imaginary values, are sine. So a plus bi equals r cosine of theta plus r sine of theta times I. So our imaginary portion, or what we might think is our traditional y-axis, and our x-axis. So sine and cosine. So it's nice to have some consistency with our trig here. So trig form of a complex number, given our complex number is z plus bi, z equals r cosine theta plus I sine of theta, where a cosine is our cosine and b is our sine. Our absolute value, r equals the square root of a squared plus b squared, and this is going to be super handy for us as well. The tangent of theta is b over a, or sine over cosine, or as we know it, y over x. So all that's consistent with our trig and what we have seen before. So our r value is the modulus of z, and theta, or our angle, is the argument of z. So our argument and angle, they both begin with a, and then our distance here is the modulus of z. So the trigonometric form of a complex number is also called the polar form. I'll show you the polar plane in our classroom, but because there are infinitely many choices for theta. Okay, so those are those coterminal angles as we continue around the unit circle or do our rotations. Okay, and they can be both positive and negative. The trig form of a complex number is not unique. Normally, theta is restricted between the angles of 0 and 2 pi. In interval form, we'll often see it look like this. Although it's convenient to use theta to be less than 0 or negative theta. So if we want to write the complex number z equals negative 2i in trig form, we want to get back to that sine and cosine. So our goal here to answer this question is to get z equals r times cosine of theta plus I sine of theta. And you'll sometimes see this as sine theta times I. I like to put the I out in front, but either way should work for you. Essentially, our z here is really 0, our cosine or our x portion, minus 2i, or our y, or our b. So 0 is our a, and b is our negative 2, or our sine. A is our cosine. So we can figure out our r pretty quickly. R equals the square root of a squared plus b squared. So that is simply the square root of 4, or 2. So now we've got our r is 2. And 2i, well, where is negative 2i? Well, if we graph negative 2i, or we graph this number, we would be down here. This is the point 0, negative 2i. So if we equate that to our unit circle, so we come around, if this were the unit circle now, we would be at 3 pi over 2. So now we know what our theta is. Our theta is 3 pi over 2. Also, backing that up, tangent is sine over cosine, or b over a, negative 2 over 0, or it's undefined. And of course, tangent is undefined at 3 pi over 2. We've got our answer here. Z is equal to 2, our r, cosine of 3 pi over 2, plus I sine of 3 pi over 2. We have got our trig form of our complex number. Sample 3, we've got a little bit more complicated complex number. We want to find the trig form of z equals negative 2 minus 2 times the square root of 3i. We want to find that in trig form. So again, our goal here is to get z is going to equal the trig form, r times cosine theta plus I sine theta. So we need a couple things. We need to get r, we got to figure out what that is, and we need to figure out what our theta is. So once we achieve those two things, we'll be in good shape. So to find r, we follow our process. We take the square root of a squared plus b squared, so negative 2 squared, plus negative 2 square root of 3 squared. We might see this as the square root of 12. You might see that. And we get 4 plus 4 times 3. And we get the square root of 16, which is 4. So our r is equal to 4. Part 2, our tangent of theta, b over a. So we're going to back into theta here. That's equal to negative 2 square root of 3 all over negative 2, which is a positive square root of 3 over 1. So think about your unit circle. Since A and B were both negative here, we're in the third quadrant. So we are actually going to be working down here. This is our y and our x, or our sine and our cosine. So we think about our unit circle, the third quadrant. Where is sine the square root of 3 and where is cosine 1? Well, that occurs at 4 pi over 3. They're both negative there in the third quadrant. Our final answer then, z is equal to 4 times the cosine of 4 pi over 3 plus I sine of 4 pi over 3. A little bit more complicated sample of trig form of a complex number, and we'll get some more practice with that when I see you in class.